Welcome everyone to this next video in which we'll continue to look at some of the basics of reverse engineering using Ghidra, and in particular be looking at basic control structures and basic data structures. So in this video we're going to focus on data structures and look at arrays. If you aren't as familiar or you haven't looked at control structures, particularly loops at a low level, then I would encourage you to watch the video that I produced just previous to this. And I've included a link here in the description. Also in the description is a link to the source code. So if you'd like to download the sample from the corresponding GitHub, that's also available. So you can go ahead and grab that and follow along here. As you can see, it's a relatively simple program. It seems very straightforward, but what's interesting about this is this actually brings up a number of different compiler behaviors that we're going to see once we reverse engineer the program. And even some issues that are currently there with Ghidra that will require you to do a little bit, or require us to do a little bit of fixing up in the output. So we'll talk about that when we get there. In terms of the program here, our goal primarily then outside of that is to understand and recognize when arrays are being used, what is the size of the array, and then what are the different sizes of the elements of the array. And our ultimate goal then with that is just to better understand how these arrays are being used in the program. Okay, so let's take a look then at the sample program. As you can see here, declaring these arrays locally, that means that the space for all of the arrays, as well as this counter variable x, will be on the stack. So we're going to see, and we can calculate here quickly, the amount of space that we should see on the stack. Now, for each array then, inside of this for loop, I'm going to just simply access each element using our counter variable and assign the value of the counter variable to that element. And so we're just going to iterate through each one of these, and we'll see that here when we reverse it, both in the decompiler output, which will give us this higher level representation, as well as the disassembler, which will, we're going to look at both because I think it's very important to understand how to read and interpret both. Since these variables are all declared locally, that means the space for them will be on the stack. So when we analyze the function, in this case main, we'll see a sub from ESP as part of the Prologue code that will allocate the space. So it's just going to decrement our stack pointer in order to account for the amount of bytes that we need for these local variables. If we add those up, we can open up a calculator, make sure that we're in base 10 mode or decimal, because I'm just going to do this math in base 10 because base 16 math is just my brain sometimes locks up when it tries to do it. So let's go through each variable, right? Int x is 4 bytes. We can then add, we have an array of 20 elements, char array of 20 elements, so each element is 1 byte, so that's just simply 20 bytes. Our next array is an array of shorts, 20 elements, so each element is 2 bytes, so that gives us 40. And then our last array is an array of integers. Those are going to be 4 bytes because I'm going to compile this for 32-bit. So those are 4 bytes each, so 4 times 20 is 80, which means that we should have 144 bytes at a minimum for our stack. You'll see that oftentimes in our reversing tools, our disassembler decompilers, that they're going to use hexadecimal for these offsets. So it's important to note that the hex value 144, or the decimal value 144, is a hex value of 90. Now, in order to compile this, you can use the developer command prompt. This comes with Visual Studio, the community edition, so you can download that, install it, and then open up the developer command prompt, navigate to the folder that you have the source code, and use the CL command. So CL and then the name of the source file. As long as there are no syntax errors, you should see output your name of the original input file, .exe, and that's our executable that will then disassemble, decompile. From there, I'm going to go ahead and create a project in Ghidra. I already had a control structures project created from the previous video, so I'm just going to add to that. And once you've added, you'll be prompted to do the initial analysis. That is just the file format analysis. Go ahead and select OK there. And then we can either double click the executable that we want to load in the code browser, or we can drag and drop that onto the dragon icon. Since we have not analyzed this, I have not analyzed this yet, simple program will go ahead and accept the defaults, and now Ghidra is going to go ahead and do the code analysis. So it's going to take just a moment here. You can watch status down in the lower right, as well as you typically get a message box about the presence or the absence of debug symbols as another kind of more visual indicator that it's complete. Once the analysis is done, we need to navigate ourselves to main because I use Visual Studio to compile this. There's that message box. There's quite a bit of code that the compiler decompiler adds. So the quickest way to do that is to open up the function node in the symbol tree window, go to entry. From the decompiler view, go down to about 3/5 of the way down. I know the function just because I've practiced this a number of times before I recorded, but if you look in the disassembly, typically the function call that is preceded by 3 pushes. That's argc, argv, environment p. Here we can see that is, of the course, the function I have already highlighted. We can double click that, and now we're in main. We can further identify that we're in main because we see the functionality that we just discussed in that original source, and that we have our 20 element arrays of different sizes defined here, as well as our loop that is going to access each element of each array. So let's start at the beginning of this function, because there's a couple of things that we need to deal with or address before we can get too far with our analysis. And this is just a current inconsistency with the version of Ghidra that I have, and it should actually be the latest version. Here it is, just in case I might be a version off. But here it is, just for, I guess, posterity. We can look at the function Prologue, and the function Prologue is the first few instructions that sets up the frame, the stack frame, for that particular function. The stack frame, very simply put, is just the region of memory that the function utilizes for its execution. So it's the arguments that are pushed on before the call, it's the return address from the call instruction, it's the old value of EBP, so that way it can be restored when the function returns or unwinds. We then move into EBP ESP, so that creates the base for our new stack frame. And then there's a sub from ESP for any local variables that we need in this particular function. Now, the stack, we typically think of the stack conceptually as something that grows. We push things onto it, it gets bigger, we pop things off of it, it gets smaller, and that's true. But in terms of the actual virtual memory space, the addresses that we use, the stack grows from a higher address to a lower. That's why in the Prologue, we are subtracting from ESP a value of 94 hex. So our stack pointer, our stack gets bigger, and we decrement from our pointer. Now, a couple of things happen here when we do that. One is that we simply are just changing where ESP is pointing to. So if that region of memory on the stack was previously used, then there's still going to be content, oftentimes unpredictable and random, in memory. And so if we don't initialize our local variables or clear that memory out, if we try to use it, it can lead to problems, unexpected behaviors in our program. It's commonly referred to as uninitialized variables. One thing that I failed to point out here when we looked at the original source is that I have this additional syntax as I declared this integer array. I said equals bracket 0 bracket. I didn't do that with the others. And what this ends up doing then is it zeroes out all of the memory for this array. So that way, before it is used, before I use any element, it ensures that it goes through and zeroes them out. With these other elements, with these other arrays, this is not happening. And so we'll see how this is actually implemented here in just a moment. Okay, another thing we need to take note of is we have a sub from ESP of 94 hex. Now, we just did the calculation and we came up with a value of 90 hex. So we're subtracting 4 bytes more, 94 instead of 90, so 4 bytes more than what we originally calculated. And the reason that is happening is due to, as you can see, both in the disassembly and the decompiler output, that we have this instruction right here that does an XOR, and then we have this function call, and they're 2 separate things. This is actually our stack cookie, or our stack guard. So the compiler has determined that there is a buffer. Of course, that we have several buffers, several arrays. And because of that presence of that buffer, it's going to add a cookie or a check value. And that check value will be placed at the end of the array. And then that way, if an overflow occurs, if we corrupt 1 bit of this cookie value, that value will be calculated and checked again when the function returns. And if it's not the same, that means it was corrupted, then the function can terminate, the program can terminate, and we're preventing, hopefully, the abuse of the program from exploitation. You'll see then that we move into EAX, this value from memory, and this is going to be initialized. You see all that code that we had before we got to main. Part of that is responsible for creating this cookie value. It's moved into EAX, and then we XOR that value with EBP and store that value in EAX, and then we move that value in EAX into the stack, into a local variable. So the addition of that stack guard is why, or that stack cookie, it's canary token, it's called many different things. That's where we get this additional 4 bytes than what we originally calculated. So this value here is updated, and then at the end of our function, it's used again, it's moved into ECX, we XOR the value, and then it's checked to see in this function, it's checked to see if it's the same. And again, if it's not, then the process will terminate, the program will terminate. Otherwise, it returns and it exits, in this case, as it normally would. If it were, if there was another function call, it would just return to that function call. So we have some additional functionality here that is a part of that. Now, the other thing that you'll notice is, well, let's first take a look at this function call right here. And then we'll come back and talk a little bit about some problems with the stack layout. So with this function call, what we're seeing is now we're pushing onto the stack a value of 50 hex, we're pushing 0, and then we're loading the address into EAX of a local variable. So EBP plus and some offset, a negative offset. Remember that when we create the base of our stack frame, then we're using EBP as the base, and we're referencing arguments and local variables relative to EBP. So the higher the stack we go, we have to use a larger negative offset. The lower on the stack we go, we can use a positive offset. So positive offset to get to arguments, negative offsets to get to those local variables. Ghidra has decided to display this as a hexadecimal signed value, but we can go down to the convert menu and we can change that to any different number format we want. In this case, we can say signed hex. And so what it's saying is at an offset of EBP plus minus 90 hex, load that address, LEA, load effective address, load that address on the stack into EAX, and then push it for our function call, right? And that's what this syntax looks like at a little bit higher level in the decompiler. Now, we don't know precisely what this function is, but we know that we now have an address on our stack, we have a 0 value, and we have potentially the size of our array. If you think about the size of our array here. So we calculated that earlier, and we said that we have 80 bytes. Let me put that in base 10. 80 bytes. In hex, that would be 50. So this looks like, of course, that matches up, and it is. So it's doing a memcopy or a memmove, and it's going to start at the base of the array, and it's going to write 0, 1 byte at a time, for 50 bytes. Now, sometimes you'll find that when doing static analysis, it is very helpful to also complement it with some dynamic analysis. And so I thought it would be interesting here to just take a moment and actually look at this memory in a debugger. So I'm going to go ahead here and open up x64 debug. I've just downloaded the latest stable version. You can, once you've extracted that archive, you can run either directly which version of the debugger you want, x32, x64. This is a 32-bit program, so I'm just going to launch the x96 debug, which will allow me to choose the launcher. So we'll do 32-bit. From there, go to File, Open, and there's our arrays. So double-click that. Now, with x32, x64 debug, when you load the executable, there is an initial break, which means that it's loaded the program into memory, but it hasn't begun execution. So that's the system breakpoint. That allows us to set breakpoints, and this is a very common debugger behavior. Now, if we type in G to go, that will begin execution. And what x32 debug does here additionally, that not every debugger does, is it breaks at the entry point. So here we have a call and a jump. If we follow that jump, which we can just step into, then we're in that initial bit of code, the start that we saw earlier with Ghidra. And so now what we can do, if you remember the address where main is at, you could just set a breakpoint there and navigate to that, allow execution to roll to that. Or we can just scroll down a little bit until we get to our 3 pushes and then our call, which is right here. So I could set a breakpoint by just toggling or clicking the little dot on the margins there, and that'll toggle that breakpoint. You'll also notice that the address BA1000, if we go back to Ghidra, that the beginning of this function is at 401000. And the reason that that is different is because this program is using ASLR by default. And so the upper 4 bytes of the 8-byte, no, I'm sorry, the upper 2 bytes of the 4-byte memory address is being randomized. So that's why we're getting these different values. If you get tired of dealing with ASLR when you're debugging these learning, these toy programs, you can use editbin to disable ASLR, and I don't have the command off the top of my head, but if you do a search for it on your favorite search engine, you'll be able to find that. Otherwise, you just have to be able to make the translation. So just recognize that these are going to be different addresses when you run the program. So now that we've set our break, we can resume execution. We can hit our breakpoint. We can see very clearly that we've hit that breakpoint. Now we can step in and we can look at setting our next breakpoint. For this one, I want to set the breakpoint right before the call to where it zeroes out the memory. So whether it's the LEA or the push, I'd already run this before, which is why you see this breakpoint on the push, and that's fine. So what we can do now, confirm that breakpoint is set, it's enabled, and resume execution. LEA into EAX are EBP minus 90. So that's getting the address for the location on the stack of EBP minus 90. And we should see that now in EAX, which we see over here in this registers window. What we can do is we want to look at the content in memory as it currently sits. So we can right click on that address and select follow and dump. And what that will do is down below, it'll update this dump window, this memory window, to begin at that address, 95F800, and it'll just show us, like it would in a hex editor, the contents of memory. So you can see that there's quite a bit of just random stuff there because this memory had previously been used and not cleared or zeroed out. It's very uncommon for that to happen unless explicitly done so in a program. Now if we step, we did our push. Now we'll do our call. And what you want to pay attention to is that the first 80 bytes here in the window will now get zeroed out, as you can see here. Right. So if we weren't able to use or apply signatures to help understand what that function is, or we weren't able to understand based off of our program analysis and the arguments of the function what it was doing, oftentimes doing a little bit of dynamic analysis can go a long way in helping to really understand what different parts of a program, different parts of code, different series of instructions are doing. All right, so let's close that. Let's go back to our program now. Now, I mentioned there's a couple of additional things that we need to address here. And one of the things is that this is actually incorrect. What we have our stack is once we've entered the stack frame, we have pushes from any arguments. We have then the call instruction, which pushes the return address on. We then push the old value of EBP before we move into EBP ESP. Right, and then it's at that point that we begin subtracting from ESP for our local variables. And so at this point, we have, the stack pointer is pointing to our previous value of EBP. And so anything that is a local variable will be at an offset of +4. Now, one of the things that the compiler will do when it determines that there is a stack cookie is it will reorder your variables. And it'll say any local variables are going to be higher on the stack above our arrays or our buffers. That way, if a buffer is corrupt, the buffer will overwrite the stack cookie and not a local variable so that we can determine when the function returns that a corruption has potentially occurred. If it didn't do that and it left those local variables below the buffers, then you could potentially overwrite that local variable without overwriting the stack cookie. So you could still potentially change or modify the behavior of the program. Now, with this one, what we see here is then that our stack cookie should be below our actual buffers, our arrays. And it's at the wrong offset. It's at what it's been determined in the output here is that it's at an offset of +8. So local underscore, and then the default convention is to use the offset, so -8. And that's not actually where it exists. Now, I just know that, and that's what stuck out to me, that this seems to be wrong, because when analyzing the stack frame for this function, the stack cookie typically then comes right after we base the frame, which means that it should be an offset of -4. If you're not sure, you can use other disassemblers. IDA Pro, Binary Ninja, Radar 2, your disassembler or your debugger that we were just using would also show us the instruction, and we'd be able to then maybe recognize that we have a slight discrepancy here. You can also look at the opcodes. So you could take these opcode bytes and you could just disassemble those, and you'll see actually one way to kind of force Ghidra to reanalyze is to highlight this section. You can right click and clear code bytes, or you can do C as a shortcut key and then D to disassemble, and you'll see that it removed the label. So it removed the label that it tried or that it created for the stack variables. But now we see that it is obviously EBP plus -4, right? So it's a bit of a problem. If you look at another thing you can look at, if we right click on the function and we go to the function menu and edit stack frame, you'll notice that this gives us a view of the stack frame and all the local variables. Its lowest offset is -98 hex. It also then uses that 98, 94, local 8 in order to identify potential variables for us in this frame. You'll notice though that we have a sub ESP 94, right? So the most that we subtract overall for this function for those local variables is 94 hex. So it's 4 bytes off. Again, I can't say 100% what is the root cause of that discrepancy, and I went back and forth on even producing this video because of it. But you know, it certainly is something that you're going to have to, that you will encounter, and I'm certain these bugs will get worked out. But you know, until then, they're just the reality of using some of these tools, right? So that's why I feel it's important to have a really good understanding of being able to analyze the program, the assembly, the decompiler output, and just really understanding what's going on here. So okay, so we've addressed that discrepancy by renaming this one. That actually fixed that discrepancy because that was 4 bytes off. And essentially, all of these locals that we see here are 4 bytes off. They're 4 bytes lower on the stack than they should be. Now, you may be saying, well, what does it matter? I mean, if I'm analyzing the program and I can still determine the functionality, then it doesn't matter if it's 4 bytes off. And that may be the case. But certainly, you know, I find it oftentimes that you do need to be very, very, very precise. And so identifying that discrepancy and fixing it is something that is helpful. This issue will come up again. In fact, this is another kind of artifact or residue of that problem, and that we are LEA into EAX local 94. Well, this isn't local 94; it's actually local 90. So we could, if we go to edit label, or we just hit the L key, we can fix the label. Although we can't use the default naming convention. So if we just try to do local _90, Ghidra says, nope, that's reserved for me to use, not for you. So we could do, I don't know, let's say real. It's really local _90. Okay, so let's continue to come back and really talk about this issue, and I'll show you how, if you analyze the stack and the stack frame, and again, you'd be able to recognize these things if you hadn't initially. All right, so we saw how this is going to zero out memory. After the call to zero out the memory, we add to ESP value of hex C and hex, which is just to count for the 3 pushes. So each push is 4 bytes, so 4, 8, C. That just clears that up. And now we're ready to get into our loop. So we can analyze our move into EBP plus local 98, a value of 0. Now, again, this is not local 98. And if you weren't entirely sure, we could clear the bytes, disassemble. We'll see now we have a move into D word pointer EBP plus, and this hex value. This is the signed representation of, well, it's not the signed representation, it's just the raw 2's complement version of that hexadecimal value. If we go down to convert, we can tell it to show us that in signed hex, right? So now we can see that, yeah, in fact, it is at an offset of -94. And that makes sense because then that lines up with the analysis that we've done previously and the total size of our stack frame. You'll also notice, so we can go back to the stack editor window. Again, keep in mind that now we're 4 bytes long on this display, but this variable here, this is our integer x. And even though in the original code, we define that first. There is a tendency with at least the compilers that I've worked with that they are initialized or the stack space is made available based on the order that they are initialized. That in this case, because of the compiler determining that there was a buffer and the need for a stack guard, it put the variable at the very top of the stack. With our buffers then, right, the stack grows from higher addresses to lower. That means that to get to the top of the stack, we need a larger offset to get to that lower address. That means that our buffers are going to be then below this local variable, int x. Our buffers then, the first element begins at the lowest offset, the highest spot on the stack, and then we write down the stack to higher addresses until we reach the end of the buffer. Now, if you continued to write a buffer and there was an overflow, then you would write where you would start corrupting the return address and EBP, and you would continue to go down the stack. So if our stack cookie is down here at an offset of -4, not -8, if we corrupt that, check the value and return, that's how the function knows if there was potentially a corruption. Okay, so that's some of the variable reordering that is being done simply because of the identification of a stack guard. Okay, so now we moved into 0 at an offset of EBP -94. That's our local 8 as it's labeled here. It's really local 4. And that's initializing our counter variable for our loop. You'll notice that the loop here, even though it was a for loop, it's been decompiled as a while loop. And I'd get into a little bit more detail in the last video. So if you're curious to dig a little bit deeper into that, I would encourage you to check out that video. After our counter variable is initialized, we have an unconditional jump. This unconditional jump takes us to the comparison, the conditional test. Before then, we either enter the loop. So if we don't jump, we enter the loop. If we do take the jump, the conditional jump, then we are done. We're going to break the loop and we're going to continue to do our cookie check thing and return. Okay. Inside the loop, though, that's what we're the most interested in, and in particular, identifying the use of the arrays. So we're moving our local variable into EDX, EBP plus local 98. I'm not going to do this for everyone, but again, just to reiterate, you can clear, you can disassemble, you can then convert this to a assigned hex offset, and there's our -94. Right, so that aligns with what we were expecting. So we move into EDX, our counter variable. We then move into AL, our counter variable. And our next instruction is where we access the array. So why did we do these two instructions before? Well, it all is how the calculation is being set up to access each element of the array. Now, of course, when we are doing program analysis, you're going to encounter array usage, and it's not always going to be clear-cut, right? This is very clear-cut in the sense that we're looping through every single element, right? So the identification can get a bit more complicated. But what you oftentimes see is that in order to access certain elements of an array, one way to do that is to go from the base of the array, where it is on the stack, and then calculate the appropriate offset to get to that element. And that's what we're seeing right here. So EBP is the base of our frame, -18 hex is the beginning of our actual, this first buffer, this first array. We can calculate that if we go back to our stack view. So -18 hex, remember -4, not -8. And if we do the math on that, so 18 minus 4 equals 14. Sorry, let's do that in base 16. So 18 minus 4 is 14. In decimal, that's 20. And that's the size of the array that we originally calculated, and that we have an array of bytes of chars, it's 20 elements, that's 20 bytes. So as you can see here then, the first element is going to be at the lowest address on the stack, so the highest part of the stack for that particular array, and then we're going to calculate addresses down until we get to the end. So EBP, -18 hex, that's the base of our array. EDX, if you look at what was previously in EDX, and we can hold the command key on a Mac or Windows key, I believe, on a Windows system, we can see that we moved into EDX our cookie or our counter value. So our counter value is in EDX. We then multiply that by 1. Okay, and what this is doing then is this is the size of the elements of the array. So this is what is indicating to us that we're dealing with an array of bytes, because each element is only one byte wide. So we take our counter variable times that, and then we add that to EBP, and then we subtract 18 hex. So if you think about that, the first value of in EDX will be 0, because that's what we just initialized that counter variable to. So 0 times 1 is 0, so we're at the first element, right? EBP plus minus 18 hex. If we then get to 1, we take 1 times 1 is 1, we add that to EBP, we minus 18 hex. So now we've moved to the next element. We've actually gone a bit higher on the stack because we've added that value. This just continues in this fashion. Now, as we iterate through the loop, EDX continues to increment by 1, the value continues to go up, and we just calculate to the next element. You'll notice with the output here, we have the 3 dots, and so we can't necessarily see everything. The only way I have discovered, and maybe I just haven't looked hard enough to see the entire statement, I think you can hover over it. I think that's kind of annoying though. And so you can open up under Windows the disassembled view. Right, and this is another way to see that. So now we can see that the only part we're actually missing is that we're moving AL into this address that we calculate and then dereference. Right? So we calculate the address and then the brackets dereference. AL, that was the second move instruction in the beginning of the loop. So we moved into AL, our local counter variable, and you'll notice that since we are dealing with an array of bytes or an array of chars, that whatever value is here, we're only reading the first 8 bits. We're only reading that byte value and moving it into AL before AL is moved into this stack variable. So if we happen to be pointing to a value that was larger than what a byte can hold, we would just be truncating that data. Okay, you'll also notice the syntax before both of these dereferences, byte pointer. And what that's telling us is that at this location, we can only access up to a byte's worth of memory. So you'll see that byte short, well, in the assembly syntax, you'll see byte word, D word, quad word, things like that. In the higher level language like C and C++ and others, you'll see more data types like short and int and char. If we move on then, we're ready to do the next assignment, access the next array. And you're really going to see essentially the same pattern. There's just going to be a couple of small differences. We're moving our counter variable into ECX, and then we are moving our counter variable into DX. Right? DX is half of our normal 32-bit registers. So we're dealing with our short array of shorts, which means we have 16 bits or 2 bytes, and DX is, of course, those represents those 2 bytes. So ECX then will be used as it was previously in order to calculate the element of the array. So the counter variable times the size or the width of each element. So an array of shorts will have a value of 2 here. So that value times 2 plus EBP minus the base of this array. And this array is at an offset of 40 hex. Again, we can calculate that just to make sure that it in fact adds up. If you add, well, there's a number of ways we could go about this. Our previous array started at an offset of minus 18 hex, and this one is at an offset of minus 40. So we'll stay in hex mode. We'll say 40 minus 18. Decimal is 40. Right, so we calculated 20 element array, 2 bytes per element is 40 bytes. That means that we have 40 bytes between the beginning of that array and the end, right, and the next array. So that adds up. After that, though, just like the previous, we move DX into that location, and we only have a word's worth of memory, so 2 bytes worth of memory there, which is what this is telling us. This pattern continues one more time, and the only difference again is where our array starts and then the size of each element. Since this is an integer array, we have a size of 4, so we're multiplying our counter variable times 4. And then for whatever reason, Ghidra decided to display this as, again, in the kind of the 2's complement version. So with 2's complement, the leftmost bit determines whether or not it is signed or unsigned, and then you have to invert all the bits and add 1. So that's why you have all these Fs. A low numeric value that's negative, when we invert all the bits, it sets all of these upper bits to 1. And this is usually an indication that you're dealing with a signed value. We can convert that, signed hex minus 90, which again makes sense if we look at our stack frame. I said minus 94 is really our counter variable. And so minus 90 then is the beginning of this particular or the last array. If we do the math on this one as well, we can take our beginning offset of 90 and subtract from that 40. We get a hex value of 50. In decimal, that's 80, and that was the size of our array. We had 20 elements, 4 elements each, so we need 80 bytes. So again, it all adds up there. As with this one, we're just moving ECX. So we moved our counter variable into ECX here, and then we move that into the dereference location for our array. And then again, as this loops through, we're just incrementing our counter variable, and that is changing the calculation appropriate to the size of each element. Okay, and that's really a lot there to help get you oriented with analyzing arrays, especially with using tools like Ghidra, looking at the disassembly, looking at the decompiler. We talked a little bit about some issues or some discrepancies in the output and ways in which at least I identified that, and then ways to fix that so that you can ensure that your program analysis is accurate. Hope you enjoyed this video, and we'll continue to explore some of the basics of reverse engineering with Ghidra here in upcoming videos.